Digital computing systems use the binary system to represent numbers and, consequently, to perform arithmetic operations using binary arithmetic. In the next part of the course, we will focus on computer arithmetic, and in particular on number representations and on algorithms and hardware architectures for arithmetic operations. This video will briefly review integer representations, which you should already be familiar with. In the following videos, we will explore various algorithms and hardware architectures designed to perform the four main arithmetic operations on both unsigned and signed integers. Finally, we will discuss the representation and processing of real numbers. These videos are not intended to provide an exhaustive treatment of arithmetic for computing systems, as such a treatment would go beyond the scope of this course. Instead, we will approach the design of arithmetic units from a different perspective, focusing on the identification of design patterns that arise not from a direct synthesis of truth tables through a straightforward application of the methods presented in the previous part of the course, but rather from an analysis of the algorithms used to perform each operation. We will see how the regularity, modularity, and scalability of the implementation with respect to the number of bits used to represent the operands are essential characteristics of the modules we will study. As we already know from previous courses, an unsigned integer value is represented by a vector of n bits. The value of n determines the numerical range of representation, which spans from 0 to 2 to the power of n minus 1. Binary encoding is a positional code, where each bit contributes a value that depends on its position. Specifically, it corresponds to increasing powers of 2, from 2 to the power of 0 up to 2 to the power of n minus 1. Let's consider the example shown here. 1 0, 1 1 0. First, note that with 5 bits we can represent unsigned integer values in the range 0 to 2 to the power of 5 minus 1, which is 0 to 31. So, it is easy to compute the decimal value of such a number by multiplying each bit in the vector by the corresponding power of 2. Thus, the result is 22. Let's now consider the problem of representing signed integers and therefore also negative values. There are two main methods for binary representation of integer values: the sign and magnitude representation and the 2's complement representation. We'll start with the sign and magnitude format, since it is the one that most closely resembles how we deal with numbers in everyday life. In this representation, if a number is encoded using n bits, only n minus 1 of them are used to represent the magnitude, that is the absolute value, while the most significant bit is used exclusively to specify the sign. 0 indicates a positive number and 1 indicates a negative number. This representation allows encoding values in the range from minus 2 to the power of n minus 1 plus 1 up to plus 2 to the power of n minus 1 minus 1. However, it introduces a double representation of 0, which occurs both with all bits set to 0 and with only the most significant bit set to 1 and the rest to 0. Finally, to compute the opposite of a number, it is enough to flip the sign bit. Let's now look again at the same example of the previous slide, but now assuming it represents an integer value. We can immediately notice that the most significant bit is 1, so the number is negative. To determine its absolute value, we just examine the remaining 4 bits, which give us the value 6. Therefore, in sign and magnitude representation, the bit string 10110 represents the number minus 6. Although sign and magnitude might feel more intuitive, it turns out to be less convenient when it comes to performing arithmetic operations. The second representation of signed integers addresses some of the issues seen in sign and magnitude representation. This representation is called 2's complement. Here we still use the positional binary encoding seen for unsigned integers with one key difference. We consider the weight of the most significant bit as negative, that is minus 2 to the power of n minus 1. Even in this format, the most significant bit can still be used to determine whether a number is positive or negative. However, Unlike sign magnitude representation, in 2's complement, the most significant bit also contributes to the magnitude of the number. In conclusion, the sign and the magnitude are encoded together in a single bit vector. Moreover, the range of representable values is slightly extended by 1 unit, only on the negative side. This is due to the fact that 0 has a single representation based on a vector with all bits set to 0. To compute the opposite of a number, we flip all bits, changing every 0 into a 1 and vice versa, and then add 1 to the result. Let's once again take our 5-bit example, and now compute the value of the same bit sequence using 2's complement encoding. We observe that the most significant bit is 1, which again tells us the number is negative. However, unlike the previous case, to determine the complete value, we must also include the contribution of the most significant bit, which now has a negative weight. So the numeric value represented by the bit string 10110 is -10.